In this video, we're discussing ordinary differential equations. In particular, we're talking about solution methods for initial value problems. And here we're going to discuss stability analysis for the implicit Euler method. So the implicit Euler method was introduced in the previous video. The stability analysis for this method follows by applying it to the model equation x prime is equal to lambda x. So for implicit Euler, the method proceeds with the expression shown here. So xn plus 1 is equal to xn plus h times f evaluated at xn plus 1 and tn plus 1, where h is the step size. So applied to the model problem, this expression yields what is shown here. So xn plus 1 is equal to xn plus h lambda times xn plus 1. And we can rearrange this for xn, and we see that we get xn plus, we rearrange this, for xn plus 1, and we see that we get xn plus 1 is equal to 1 minus lambda h to the power minus 1 times xn, or xn over 1 minus lambda h. So as we proceed, we can see that our value at a time step n, or xn, can be written as sigma to the power n times our initial time step x0, where sigma is equal to 1 over 1 minus lambda h. And when we consider complex lambda, so lambda is equal to lambda real, or lambda r plus I lambda I, we get that sigma is equal to 1 plus the real part, 1 minus lambda r h, minus the imaginary part, I times lambda I h. The denominator here is a complex number which can be written as the product of its modulus and a phase factor. So this denominator we can write as a times e to the power I theta, where a and theta are given as shown here. So a is equal to the square root of the real part squared plus the imaginary part squared, and theta is inverse tan of the expressions here. For stability, the modulus of sigma must be less than or equal to 1. So this was our sigma. We can bring the e to the I theta to the numerator and call it e to the minus I theta. So the modulus of this has to be less than or equal to 1. So the modulus of the top is just 1. So modulus of sigma has to be equal to 1 over a, or is equal to 1 over a, which has to be less than or equal to 1. So the circle, defined by the values in a, defines the boundary of stability region, and the method is stable for values outside this circle, because you can see if we plugged in what our value for a was here, which was the square root of these values, and then square both sides and bring this here, we get that this needs to be actually greater than or equal to 1. So this means the stability region for the implicit Euler method looks like this. So when we consider lambda r being negative, we can see that this is always satisfied, so this part is always greater than 1 because when this value is negative. So that means that the implicit Euler scheme is unconditionally stable, and we can see that the entire left half plane, so any value, any time that our real part of lambda is negative, it is contained within the stability region. So unconditional stability is the usual characteristic of implicit methods, and the price for this is higher computational cost per time step for having to solve a nonlinear equation. So let's consider one of the examples that we looked at before, where our ODE is y prime plus 0.5y equals 0 with an initial condition of y0 is equal to 1. And let's solve this using the implicit Euler method between 0 and 20 using two different time steps, h is equal to 1 and h is equal to 4.2. So the stability analysis for the implicit Euler indicated that the numerical solution should be unconditionally stable. And for the implicit Euler, our solution at time step I plus 1 is equal to yi plus h times dy dt evaluated at I plus 1. So yi plus 1 and ti plus 1. So applying this to the given ODE, we see that yi plus 1 is equal to yi minus 0.5h times yi plus 1. And we can rearrange this for yi plus 1, which is equal to yi divided by 1 plus 0.5h. And proceeding iteratively, we can find the solution for t up to 20 for each of the two step sizes. H is equal to 1 and h is equal to 4.2. And if we do this and plot the solution, we get something like what is shown here. So the black is the exact solution, the blue shows the implicit Euler with h is equal to 1, and the orange shows the implicit Euler with h is equal to 4.2. You can see that both solutions are stable as expected, and the solution with h is equal to 1, the smaller time step, is more accurate. And you can go back and compare this with the same example where we used the explicit Euler method, where it was stable for h is equal to 1 and unstable for h is equal to 4.2. And we can note here that the usual difficulty in obtaining the solution at each time step inherent with implicit methods is not encountered here because the resulting equation in this example is linear. But in general, that is not always the case.